In the last lecture we had looked at some applications of Hoteling's t-square statistic, and also we had looked at how to use Hoteling's t-square statistic when we have two sample normal problem and related inference regarding that. Now what we will do today is we will look at some important properties of the Hoteling's t-square statistic, some important properties of Hoteling's t-square. Now the first property that we are going to discuss is the invariance of the Hoteling's t-square statistic with respect to a non-singular transformation. So invariance of Hoteling's t-square statistic with respect to a non-singular transformation. Now what do we mean by saying is that is the following, that suppose we have this data x1, x2, xn, the random observations from a multivariate normal distribution with appropriate dimensions and a mean vector and a non-singular positive definite covariance matrix, and let C be a non-singular matrix of constants and D be a vector of constants. Now using this C non-singular matrix and D the vector of constants, we can actually make a transformation from this x to Cx plus D, say. So suppose this all these x's are m dimensional, we will take this C to be an m by m non-singular matrix and this to be an m by 1 vector. So this is a new vector that is derived from this x random vectors. So suppose we have this x1, x2, xn. So from there we will be able to get this from x1, x2, xn, the original data. Through the transformation we will be getting a new set of observations, that is y1, y2, yn, which are nothing but Cx1 plus D, Cx2 plus D, and so on, and the last one is Cxn plus D. Now the t-square statistic computed from this x1, x2, xn is going to be the same, that is going to be computed from Cx1 plus D, Cx2 plus D, and Cxn plus D. In that sense actually t-square will be invariant, or rather I will just write that t-square computed from x1, x2, xn, t-square computed from x1, x2, xn, and that computed from y1, y2, yn, and that computed from Cx1 plus D, Cx2 plus D, Cxn plus D will be same. How do we claim this? We claim this particular invariance in the following way, that since we have made this non-singular transformation, the x random vector, the underlying random vector, will get changed to Cx plus D. The corresponding, suppose we have this x to follow a multivariate normal M with a mean vector mu and a covariance matrix as sigma, then with this transformation this mu will be changed to C mu plus D straight away, and then this sigma matrix, the associated variance covariance matrix, here we take sigma to be positive definite. So this sigma is going to be changed to C sigma C prime. Now t-square statistic comes into existence actually for testing hypothesis, null hypothesis of the form that mu is equal to mu naught to be tested against an alternate hypothesis H A, that mu is not equal to mu naught, say, right. So, where does this mu naught go to? Mu naught is a known vector. So, this known vector mu naught will be shifted to C mu naught plus D, right. Now, when we have such transformations in place, what happens to this x bar quantity? Now, x bar is the sample mean vector that is obtained from x1, x2, xn. So, this x bar is computed from x1, x2, xn, the data. So, this will be changed to C x bar plus D, and our n minus 1 S, say, with a divisor n minus 1, that is what is given by x j minus x bar x j vector minus x bar vector transpose j equal to 1 to up to n. Now, where does this gets changed to? Now, when we are looking at the transformed observations, we will have this x to be replaced by C x j plus d. Now, what happens to x bar? X bar is C x bar plus d. So, this is C x bar, this minus d, into the transpose of that. So, it is C x j plus d minus C x bar minus d transpose. So, this d vector cancels out from both the quantities, and what happens is the following. We will have here C is a non-singular matrix. So, this C can be taken out from the left, C transpose can be taken out from the right, and what we will be having is the following, that the quantity that I had written is going to be C times summation j equal to 1 to n. What remains is x j minus x bar, then x j minus x bar transpose C transpose. And what is this term equal to? This term is equal to n minus 1 times S with the divisor n minus 1, right. So, what we have seen is the following, that this quantity out here, that n minus 1 S, now with this non-singular transformation is going to C times n minus 1 S C prime. So, this would imply that this S, the sample variance covariance matrix, is going to go to C S C transpose, right. Now, once we have these things in place, now the t square computed from x1, x2, xn is the following, computed from x1, x2, xn, the original set of observations, is going to be given by t square, which is equal to n times x bar minus mu naught transpose S inverse x bar minus mu naught. So, we had seen this time and again, that this is basically that Hoteling's t square when we are looking at x1, x2, xn, n observations from a multivariate normal distribution for testing the null hypothesis mu equal to mu naught against mu not equal to mu naught. Now, where does this go to? We will have this under the transformation, non-singular transformation that we are discussing. This is x bar is now C x bar plus d. Where is mu naught? Mu naught is C times mu naught, it is C times mu naught, this minus d transpose. Now, S is going to C S C transpose. So, here what we have is, this is just C S C transpose whole inverse, and then that is multiplied by the transpose of this particular quantity. What would remain, this is d cancelling out, and we will have C x bar minus C mu naught on this side. Now, what is this equal to? This is n times, now this is, this C can come outside with a transpose, this goes here, and what we will be having here is this x bar minus mu naught. So, this C with a transpose comes here, and then we will have this term here. So, which is C transpose inverse S inverse C inverse, and then we will take C from this side as well. So, this is C x bar minus mu naught. So, this C into C inverse will give us an identity matrix. This C transpose into C transpose inverse will also give us an identity matrix. So, what we will be having is n times x bar minus this into S inverse times x bar minus mu naught. Now, what is this quantity? This is the t square statistic, which is computed from the y observations, because this is nothing but y bar, this is nothing but the mean corresponding to the y random variables, and this is the variance covariance matrix, the sample variance covariance matrix, that is computed from the y observations. That is what we had seen out here, that we have these under the transformation here that we are making, that x1 x2 xn is transformed to y1 y2 yn, and then what happens to it, the corresponding means this is the mean vector corresponding to the y observations, and this is the variance covariance matrix corresponding to the y observations. And what we have proved is that the t square computed from x1 x2 xn, which is given by this, is equal to, what is this quantity? This is the t square computed from the y observations, computed from our y1 y2 yn. So, what we have proved is that the t square statistic remains invariant with respect to this non-singular transformation. So, that was the first important property that we can say about this Hoteling's t square. Now, the second thing that we are going to say is that the t square statistic can be obtained using the union intersection principle of Roy. The t square statistic can be obtained using Roy's union intersection principle. Now, what is that? We have this null hypothesis H naught, that mu equal to mu naught. Now, suppose we take this alternate type of hypothesis H naught prime, which is A prime mu equal to A prime mu naught. This is for every A belonging to the appropriate dimension, say r to the power m, because we have got a multivariate normal which is m dimensional. So, what is the correspondence between the two hypotheses H naught and H naught prime? Now, the acceptance region, note that this is a single hypothesis here, and there are a number of hypotheses for possible choices of the A vector belonging to r to the power m on the right hand side. Now, the acceptance region, the relationship, that is what we are talking about, the acceptance region of H naught is the intersection of the acceptance regions of H naught prime for every A belonging to r to the power m. Now, what does that mean? That means that this H naught null hypothesis is going to be accepted if we have this H naught prime hypothesis to be accepted for every value of this A vector. That is, we will accept H naught if H naught prime is accepted for every A belonging to r to the power m. And that is quite obvious, because if for some A this null hypothesis is H naught prime hypothesis is rejected, we cannot take this hypothesis to be accepted. Now, this is about the acceptance region. So, the acceptance region of this would be the intersection of the acceptance region of H naught primes. What about the rejection region? The rejection region has the following relationship between the H naught and H naught prime hypothesis. The rejection region of H naught is the union of the rejection regions of these H naught prime set of hypotheses. That is, H naught will be rejected if any of H naught prime hypothesis is rejected. So, rejection of any one of these H naught prime hypothesis would lead to the rejection of the main hypothesis, that is H naught, and accordingly the rejection region of H naught would be the union of the rejection region of H naught prime hypothesis for A varying in r to the power m, right. So, this basically is what we talk about as the union intersection. It is called the union intersection principle because the rejection region is the rejection region of this H naught hypothesis is the union of the rejection region of these set of hypotheses, and the acceptance region of this H naught is going to be the intersection of the acceptance region of this H naught prime set of hypotheses. Now, what we will do is that we will basically look at when is this H naught prime hypothesis going to be rejected, on what sort of theory we are going to actually base our rejection region. So, H naught prime is my A prime mu equal to A prime mu naught. So, suppose I take this one hypothesis here, H naught prime is A prime mu equal to A prime mu naught for a particular A vector. Now, in order to test this particular hypothesis, what we are going to make use of is the following. Now, we have X to follow a multivariate normal m dimension with a mean vector mu and a covariance matrix sigma positive definite. So, we will have sigma to be positive definite out here. So, X has got this particular normal distribution. So, what happens to the distribution of A prime X? A prime X will have a multivariate normal distribution which is A prime mu and A prime sigma A as its variance, right. Now, from here what we can also say is that this X bar has got a multivariate normal distribution with a mean vector mu and a covariance matrix as sigma by n. So, this would imply that for this A prime vector, this A prime X bar is going to have this m is going to be 1, this is n 1 because this is that particular 1 by m dimensional vector. So, this also is an univariate normal random vector, random variable with mean as A prime mu, the same as this one A prime mu, and a covariance matrix 1 upon n A prime sigma A, right. Now, the variance covariance matrix n minus 1 times S, the sample variance covariance matrix, this has got a Wishart m n minus 1 times sigma. From the previous results, what we can say is that this A prime n minus 1 S times A, this is going to follow a central chi-square. That is what we had seen earlier, that this has got a central chi-square on what degrees of freedom? N minus 1 minus m plus 1 degrees of freedom, and it is going to be a central chi-square. So, this is a central chi-square on the degrees of freedom, which is going to be given by n minus 1 minus m plus 1. So, using these facts, actually we are in a position to test this particular null hypothesis. How we are going to frame that? H naught prime will be rejected if the following quantity is large, if root n absolute value of A prime x bar minus A prime mu naught, this divided by under root of A prime S A is large. Why is that so? It is simple to see that because we have A prime x bar to have a normal distribution, this A prime x bar minus A prime mu naught, that divided by this variance out here, that is going to have a normal 0 1 distribution, but this sigma matrix is unknown to us, and hence we also need to use this distribution chi-square here, and then eventually what we are going to have, this distribution is going to be a t distribution, because that would be ratio of a standard normal distribution to that of a central chi-square random variable. So, we are going to reject H naught prime if this quantity is large, that is if the square of it is large. So, we will, there is a reason why we are looking at the square of that particular quantity. this a prime mu naught whole square, that divided by a prime S A is large. Now, this is as far as rejection of this one single hypothesis H naught prime for a given a prime belonging to r to the power n. So, this the large quantity of this particular observed thing based on x1, x2, xn is what is going to lead us to the rejection of H naught. Now, what is the relationship between this rejection of this hypothesis for a particular a belonging to r to the power m and the rejection of H naught hypothesis, that is mu equal to mu naught, and what we will be having is the following, and this H naught, the null hypothesis mu equal to mu naught will be rejected if we have the supremum over A of these quantities, which is n times a prime x bar, this minus a prime mu naught whole square, that divided by my a prime S A. So, this is basically the supremum over every a belonging to r to the power m, that is for all possible hypothesis H naught prime when a varies in r to the power m. If we have supremum of these quantities for varying a is large. Now, we need to look at what is this, that is we are going to reject H naught if now n is constant, n just sits outside. So, it is the supremum over a belonging to r to the power m of this particular quantity. Now, how do we write this particular quantity out here? I will take a prime outside here. So, this is a prime x bar minus mu naught, the whole square of that divided by a prime S A is large. Now, in order to find out the supremum of this particular quantity, the supremum over this term out here, we recall that we have something called a Cauchy-Schwarz inequality. So, we may recall the following result. Recall that supremum over u not equal to 0, of course, we also will take a not equal to 0, because a equal to 0 does not mean anything, because we are going to test null hypothesis that 0 equal to 0. So, that does not make any sense. So, it is over all vectors which are non-null of this u prime v whole square, this divided by u prime a u, where a is non-singular. This is going to be given by v prime a inverse v. Now, this follows from Cauchy-Schwarz inequality, follows from the Cauchy-Schwarz inequality, straightforward. So, we have this general result that for a non-singular matrix A, we will have the supremum of this particular quantity to be given by this. Now, here we will use this result in order to find out what is the supremum of this. So, we can take here this A vector to be equal to this u vector, the v vector to be equal to this x bar minus this mu naught vector, and I will take this A to be equal to this S matrix. Now, if sigma is positive definite, then with probability 1 this sample variance covariance matrix S is non-singular, and hence this S that we are talking about, of course, is going to be non-singular with probability 1, because we have chosen sigma to be positive definite matrix. And thus, this would imply that this H naught will be rejected if we have this quantity n times. Now, I will plug in the supremum value of that. Now, the supremum value of that is going to be given by this x bar, which is v transpose, and then A inverse is our S inverse x bar minus mu naught is large, right. So, this follows from this equation that this is going to be rejected. This is coming through the H naught prime set of hypothesis, and then that is going to be rejected if this is large, or in other words if this is large, that is if what is this term equal to, this term is equal to the t square statistic only, that is if t square is large, or in other words we can plug in the constants, that is if t square by n minus 1 into n minus 1 minus m plus 1, this divided by m is large. That is if this t square by n minus 1, now this 1 cancels out and you will have this here as n minus m by m is large. Now we know what is the null distribution of this particular quantity. The null distribution under the null hypothesis, H naught mu equal to mu naught, this is going to have an F distribution, a central F distribution on what degrees of freedom? N minus m, n minus m degrees of freedom, and hence the testing is equivalent to what we have already seen. So that is why one says that this t square statistic, we have actually shown that the t square statistic for testing H naught mu equal to mu naught can alternatively be obtained through this union intersection principle, wherein you consider this set of null hypothesis H naught prime, which is a prime mu equal to a prime mu naught, and then the rejection region of that actually leads us to seeing that this basically is based on the t square statistic itself. Now next what we are going to talk about is something about confidence intervals. So we will have these terms here. That let me first talk about confidence region for the mean vector mu. Now this is what we have, that we have x1, x2, xn random sample from a multivariate normal M mu sigma, where sigma is a positive definite matrix. So we are interested actually here in giving a confidence region for the unknown vector, unknown mean vector, that is mu. Now how are we going to do that? We know that this t square by degrees of freedom n minus 1, n minus m by m, this follows an F distribution. I will just write the full form of it so that it becomes easy to frame the confidence region. Note that we will have this n times x bar minus mu transpose, then we have S inverse x bar minus mu, this term here, this is the t square statistic, that divided by degrees of freedom, which is n minus 1, that multiplied by n minus 1 minus m plus 1, so that is n minus m, that divided by m, this will follow an F distribution. Now this F distribution has degrees of freedom m n minus m, right. Now if we have this particular term to hold true, this relation to hold true, this would imply that the probability of this x bar minus mu transpose S inverse x bar minus mu, this multiplied by all these constants out here, n times n minus m, that divided by m times n minus 1, this less than or equal to f m n minus m alpha. What is this probability going to be equal to? This probability is going to be equal to f 1 minus alpha, wherein this particular term is upper alpha percent point of a central F distribution on m n minus m degrees of freedom, right. So the area to the right of this particular point is alpha, and hence the area to the left of it is 1 minus alpha. So I will just write it, that probability of an F statistic on m n minus m degrees of freedom greater than this f m n minus m alpha, this is a given point. So this probability, that is the right tail probability, this probability is equal to alpha, and hence since this has got an F distribution on m n minus m degrees of freedom, the probability that this is less than or equal to this term is equal to 1 minus alpha. So, this would imply that 100 into 1 minus alpha percent confidence region for this unknown vector mu is going to be given by the set of all mu values such that we will have this x bar minus mu transpose S inverse x bar minus mu. This is less than or equal to m times n minus 1, this divided by n times n minus m times f m n minus m times alpha. So, this is an ellipsoid. What we have is this ellipsoidal region actually is giving us 100 into 1 minus alpha percent confidence region for this mu. For every mu that is satisfying this particular condition, that it is within this particular boundary region here, we will have that ellipsoid to lead us to 100 into 1 minus alpha percent confidence region for this mean vector mu. Now, next let us move on to simultaneous confidence intervals. For certain linear combinations of interest, Now, the underlying population still is a multivariate normal. So, the population is a multivariate normal m dimensional with a mean vector mu and a covariance matrix sigma, which is assumed to be positive definite. So, we have this sigma matrix to be positive definite, and suppose we are interested in setting up of simultaneous confidence intervals for quantities of the form that it is a I prime, say mu, right. This I is for 1, 2 up to p, where this p is less than or equal to m, say. So, we have p such linear combinations a I prime mu, and these are linear combinations of the parameters. Say for example, we are interested in setting up of simultaneous confidence interval for mu 1 minus mu 2 and mu p minus mu p minus 2 something. So, we are interested in such p linear combinations of the unknown mean vector mu, and we are trying to set up confidence intervals in such a way that we want to have simultaneous confidence intervals for these a I prime mu such that the joint confidence or the joint coverage actually is at least 100 into 1 minus alpha percent. So, that is what is our objective. We have p such linear combinations, and we are trying to put up simultaneous confidence intervals for this such that the joint confidence is at least 100 into 1 minus alpha percent. Now, what we are going to do is that let I be the confidence interval for this a I prime mu component. So, if we have this I to be the confidence interval for a I prime mu, what we are trying to achieve is the following. We want to achieve the following probability statement. This is intersection of each of these I equal to 1 to p that ai prime mu, this belonging to II. So, this is an event that ai prime mu that belongs to II. So, that is II is what we have defined to be the confidence interval for that particular term out there, and then the intersection of all such events, this probability we require that to be equal to 1 minus alpha. So, we will show how we can achieve under different setups such a probability statement that the joint probability of all these ai prime mu quantities belonging to the respective intervals that we are going to create, the joint probability, the intersection of all such events is going to be greater than or equal to 1 minus alpha. So, this is a statement that we are going to make, that this basically is the joint probability statement. So, this alternatively can be written in the following form, that it is probability that this ai prime mu is belonging to this II interval. This is for I equal to 1, 2 up to p for all these linear parametric functions ai prime mu that is greater than or equal to 1 minus alpha. This basically is going to give us the confidence region for each of these p linear combinations of these mean vector mu, and we will ensure that this probability is at least 1 minus alpha. Let us take an example and then try to illustrate how this type of problems, this type of confidence intervals, simultaneous confidence intervals are achieved. Now, say suppose we are looking at, suppose we want confidence interval for say some p out of m of mu I components. Without loss of generality, we take that we are interested in the first p of those components. So, we will have this as I equal to 1, 2 up to p. So, these are mu I components. We had this, the mean vector mu was our mu 1, mu 2, mu m. So, we are looking at the first p components. Suppose these p are the important ones, and we are looking at setting up simultaneous confidence interval for mu 1, mu 2, mu p, such that the joint probability of mu I being contained in that particular interval, random interval, that joint probability is greater than or equal to 1 minus alpha, right. So, this is just an illustration. This can be anything other than this mu components also. Now, we can encounter two different cases. The first case is a very simple case. Case 1 is that suppose sigma is equal to diagonal sigma 1 1, sigma 2 2, sigma m m, right. Now, that is the sigma matrix is diagonal matrix. Now, sigma matrix being diagonal matrix implies that since we have got x to be multivariate normal with mean vector mu and a covariance matrix sigma by n, sigma, just sigma, that is, in other words, this x bar has got a multivariate normal m with a mean vector mu and a covariance matrix sigma by n. This would imply that x1 bar, x2 bar, xm bar, which are the constituent elements of this x vector, which is the sample mean random vector. So, this x1, x2, xm are independent n1 random variables, because we have sigma to be a diagonal matrix. Since sigma is a diagonal matrix, the off diagonal entries which are going to give us the covariance terms for the components of this x vector, they are going to be 0, and since the joint distribution is multivariate normal, we will have these components to be independently distributed. So, since we have this x1 bar, x2 bar, xm bar to be independent n1 random variables, in particular what we can write is that this xi bar, this would follow an univariate normal distribution with mean as mu I, which is the corresponding component in the mean vector, and this variance as sigma I, this divided by n. This is true for every I equal to 1 to up to m, and in particular this would be the case if we are looking at any p of them. any p of the components which are there in mu and the corresponding components in x bar random vector. Now from this statement out here, what we can write is the following: a 100 into 1 minus beta % confidence interval for this mu I is given by the following. It would be given by xi bar, this is the interval xi bar, minus root over Sii by n, where Sii is the corresponding diagonal element of the sample variance covariance matrix. So, this is Sii by n, that multiplied by Tn minus 1, and then we will require this to be beta by 2. I will say what this is equal to. This is xi bar plus root over Sii by n Tn minus 1, this beta by 2, where probability that a t distribution on n minus 1 degrees of freedom greater than this Tn minus 1 beta by 2, this would be equal to beta by 2. So, if we have the probability of a t random variable exceeding this Tn minus 1, so this is basically the right tail cutoff point. So, we will have t distribution is symmetric. So, suppose this is a point here, this point is my Tn minus 1 beta by 2. So, to the area to the right of that particular point is beta by 2. This is a symmetric distribution. So, we will have a minus Tn minus 1 beta by 2 point. Similarly, here the area to the left of that would also be equal to beta by 2, and hence the area in between these 2 points, which is this area, is going to be 1 minus this plus this, that is 1 minus beta, right. So, we will have this particular as confidence interval, this as probability that this mu I belonging to the random interval. Now, in terms of the random interval, this is xi bar minus square root of Sii by n Tn minus 1 beta by 2, this 2 xi bar random interval, this plus root over Sii, that divided by n times Tn minus 1, this beta by 2. So, this is that interval, this is the lower point, lower confidence point, this is the upper confidence limit. This probability is equal to 1 minus beta. So, that is fine. This is as far as the mu I component is concerned. Now, note that these xi bar quantities, they are independent due to the structure of sigma matrix that we have assumed. So, that let us denote this particular interval, what we have here, to be this our II interval, that is probability that this mu I belonging to this II, this is exactly equal to 1 minus beta. Now, similar to the one mu I component here, one can take this for every I equal to 1 to up to p. Now, because we have the sigma matrix to be diagonal, the independence would imply that probability that mu I belongs to II, this simultaneously for I equal to 1 to up to p, this is going to be given by probability, this is actually intersection of I equal to 1 to p, these events. What are these events? The events are mu I belonging to this II. Now, these events are going to be independent because we have chosen the sigma matrix to be a diagonal matrix, and hence this is going to be the product I equal to 1 to up to p of the respective probabilities, because the underlying p events with which we are looking at the intersection, they are independent events, and hence we will be having this as mu I belonging to this II. Now, we have obtained these probabilities. Now, II is given by this particular random interval, and what we will be having is the coverage, that the probability that mu I belonging to a particular II, that probability is 1 minus beta. So, we will have this as 1 minus beta whole raised to the power p. Now, what do we require? we require, in order to set up a simultaneous confidence interval, see here what we had stated out here, that in order to give us the simultaneous confidence interval, we would require this statements of this type, that probability that ai mu belonging to I for I equal to 1 to p, this is greater than or equal to 1 minus alpha. So, for the given problem, if we set this 1 minus beta to the power p to be equal to alpha, then we will be able to achieve. So, we set this to be equal to 1 minus alpha, and then we can solve for beta, and then that solution beta would lead us to the simultaneous confidence interval. That is, we set here 1 minus beta to the power p to be equal to 1 minus alpha, that is 1 minus beta to be equal to 1 minus alpha to the power 1 upon p, that is what we have is this beta to be equal to 1 minus alpha to the power 1 upon p. So, from this statement out here, what we will be able to do is, given alpha, this alpha of course lies between 0 and 1, that is associated with the 100 into 1 minus alpha % confidence region. So, given this alpha, obtain beta using this particular equation, because you know what is p, we know how many of these components we are actually trying to include in the joint confidence interval. So, we can obtain beta from here, and then using that particular beta, what we will do, we will go back to this particular equation here, where we can easily obtain what is an 100 into 1 minus beta % confidence interval for mu I. So, we can use that beta in this statement out here, and we will be able to find out the confidence interval corresponding to that particular mu I component. And once we have the confidence interval corresponding to one mu I component, we can use that in the statement out here and get an 100 into 1 minus alpha % simultaneous confidence interval for p of these quantities here. Now, this p can also be all the m quantities, all the m components, right. Now, make a note of the following observations. Now, since we have 1 minus beta to the power p is equal to 1 minus alpha, this would imply that 1 minus beta is going to be greater than 1 minus alpha, because beta, both alpha and beta, they lie between 0 and 1. So, we have 1 minus beta, a quantity raised to the power p, that is equal to 1 minus alpha, and hence we would require 1 minus beta to be greater than 1 minus alpha. That is straightforward. Number 2 is an important thing, is to look at the comparison between these simultaneous confidence intervals that we are setting up for each of these p components here, and then we would like to compare this confidence interval that we are obtaining through this simultaneous approach to that of the confidence interval 100 into 1 minus alpha % confidence interval for a particular mu component only, right. So, the difference here is that in one confidence interval we are setting up a 100 into 1 minus alpha % confidence interval for mu I only, and in the second we are obtaining a 100 into 1 minus alpha % simultaneous confidence interval for p mu I components, in which mu I is one of them. So, what does the intuition say? Basically, the intuition will say that the confidence interval where we are only concentrating only on one mu I component and then setting up 100 into 1 minus alpha % confidence interval for that is going to be shorter than the simultaneous confidence intervals for p such components, and we are going to have 100 into 1 minus alpha % simultaneous coverage for all those p components. So, the intuition would suggest that the expected length of the confidence interval when we are looking at the simultaneous 100 into 1 minus alpha % confidence interval, that is going to be larger than the one when we are concentrating on one such mu I component. Let us see how we can prove that intuition of ours. So, we have, in order to prove that, we start with this particular equation here, that 1 minus beta is greater than 1 minus alpha. This would imply that this beta is less than alpha. Now, if beta is less than alpha, this would imply that this beta by 2 is less than alpha by 2. Now, this would further imply that T n minus 1. Now, let us try to find out the logic behind this particular relationship. We are trying to find out the relationship between these two cutoff points. How does this the relationship between these two cutoff points come across? Suppose this is the T distribution PDF, it is symmetric around the point 0. We have here a point. Now, what do we have? Beta by 2 is less than alpha by 2. So, we have 2 points here, beta by 2 is less than alpha by 2, and these are going to be 2 cutoff points. So, suppose I take this particular region here, beta by 2 is less than alpha by 2. So, I take this region here to have an area which is beta by 2, and then the area which is actually coming from the right of this particular point. So, this entire point here is alpha by 2. So, we will have beta by 2 which is to the right of this particular point here, having an area to the right beta by 2, and the area to the right of this point here, first point, which is alpha by 2. So, since beta by 2 is less than alpha by 2, we will have this point as T n minus 1 beta by 2, and this point is T n minus 1 alpha by 2. So, we will have this T n minus 1 beta by 2 cutoff point to be greater than T n minus 1 alpha by 2. So, we will have this particular relationship, right. Since we have this particular relationship, it is now easy to see what is the expected length of the two types of confidence intervals that I was talking about. So, this is going to be the following, that length of I that we have already constructed is given by 2 times n minus 1 beta by 2, this is SII by n, right, and length of confidence interval 100 into 1 minus alpha percent for mu I only is going to be given by similarly 2 into n minus 1. Since we are looking at mu I only, this is going to be given by T n minus 1 alpha by 2, and the multiplier is exactly the same as this. Now, since we have T n minus 1 beta by 2, as we have seen T n minus 1 beta by 2 to be greater than T n minus 1 alpha by 2, expected length of the confidence interval, expected length of this II is going to be greater than the expected length of the confidence interval for mu I only. So, this basically justifies our intuition that we said that our intuition suggests that if we are trying to make a 100 into 1 minus alpha percent confidence interval for mu I only, then that is basically taking care of one mu I component, and if we are going to have a simultaneous confidence interval for p such mu i's and trying to ensure that for all those p components the coverage that mu I belongs to respective I interval, that simultaneously the simultaneous coverage probability is 100 into 1 minus alpha percent. Now, that is going to look at p such components, and this is going to look at only one mu I component, and hence we would require in the simultaneous confidence interval set a larger interval, larger in the sense of having the expected length of that II to be higher. So, this basically tells us that if we are looking at such simultaneous confidence intervals, the expected length of that confidence interval is expected to be higher. So, we will stop here today. We will look at in the next lecture what happens if sigma is not necessarily a diagonal matrix. So, we will consider a general positive definite matrix and then look at how to construct such simultaneous confidence interval for mu I components, or in general for linear combinations, p such linear combinations. Thank you.